Hello, my name is Janus Varmaken. Thank you for listening in to our presentation of our paper, The TV is Smart and Full of Trackers, Measuring Smart TV Advertising and Tracking. This is joint work with my co-first author Hugh Ley, Anastasia Shuba, my advisor Professor Athena Markopoulou, and Professor Zubair Shafiq. Smart TVs, or also referred to as connected TVs, are internet-connected TVs with computational capabilities. This allows the TV to download content off of internet servers and run interactive apps. Smart TVs come in two flavors. There are built-in smart TVs where the hardware and software is integrated into the TV set, and there are external box or stick solutions that are then inserted into a port of a traditional TV. We refer to both of these as smart TVs. There's already a wide selection of smart TV vendors and platforms in the market. One example is Samsung's line of smart TVs, which run the Tizen operating system. Smart TV apps are both paid and free. Examples of paid apps include subscription-based services such as Netflix. Examples of free apps include Crackle and Pluto TV. The vast selection of free apps are usually monetized through advertisements, and this is usually done by the developer integrating libraries that then contact advertising and tracking services on the internet. We use the term ATS to refer to these services. Our study is motivated by the fact that smart TVs are now widespread in the US, so there's at least one smart TV in 4 out of 5 US households. Naturally, this represents a platform with a large audience for targeted ads, and the smart TV is uniquely positioned in terms of tracking, given that it can observe the user's viewing habits and then target the ads based off of that information. Furthermore, a recent paper from IMC showed that smart TVs are the IoT device that contact the most third parties, suggesting that a significant amount of tracking is going on this platform. We are further motivated by the related work. The advertising and tracking services ecosystems of the desktop and the mobile platforms have been studied extensively in the past, and there are tools available that operate on fine-grained information such as HTTP data and then block ad and tracking traffic based off of that. However, the smart TV advertising and tracking services ecosystem has not been studied until recently, and the tools available are in general limited to only operate on coarse-grained information such as the domain names. While this paper was in submission, 2 other papers were made public. Wang et al. Studied the behavior of smart TVs when used by real users, and Mokaram et al. Instrumented 2 smart TV platforms in a lab setting. Our work presents a holistic view, as we do both. So with that, our research questions become the following. What does the smart TV advertising and tracking services ecosystem look like? To answer this, we take a network measurement approach. We analyze data collected from smart TVs used by real users. We refer to this dataset as the in the wild dataset. Further, we instrument 2 smart TV platforms in a testbed setting and analyze the traffic collected from this instrumentation. We refer to this dataset as the testbed dataset. Second, we ask how effective are existing privacy-enhancing tools. Here we analyze DNS-based block lists, as these are universally applicable across all smart TV platforms. We also use these 4 block lists to label domains in our datasets as advertising and tracking services or not. This is used throughout our analysis of the traffic data. Our in the wild dataset was collected from 41 US homes. This was done by Minim Inc., who then generously provided us with this dataset. Minim collected flow-level summary logs at the home gateway. These logs contain information such as the external endpoint of the flow and the traffic volume. Given this dataset, we singled out the smart TV traffic and analyzed only that. This leaves us with 57 smart TVs and the traffic over a 3-week window. Our dataset contains traffic from smart TVs spanning 7 different platforms, as shown here. We first analyzed the top 30 most contacted domains in our in the wild dataset. ATS domains are highlighted in red and non-ATS domains in green. Here we show examples for Samsung and Roku, but the trends are similar for the remaining platforms. As is to be expected, we observed that some of the domains that rank highest pertain to popular streaming services. We also see ATS domains that are well known from the desktop and the mobile advertising and tracking services ecosystems. One example is subdomains of Google's doubleclick.net domain. More interestingly, we observed that several ATS domains are unique to each individual smart TV platform. These domains pertain to the platform operator, and this suggests that the Smart TV ATS ecosystems differ across different Smart TV platforms. The In the Wild dataset is nice in that it provides insights into the real-world behavior of smart TVs. However, the dataset does not provide app-level granularity, and it is therefore not possible to discern if advertising and tracking is a general theme on the platform as a whole, or only due to the behavior of select few apps. Furthermore, the In the Wild dataset is biased by the viewing habits of the users, and there is no obvious way to normalize this. To deal with these limitations, we instrument two Smart TV platforms, namely Roku and Amazon Fire TV, in a testbed setting. We picked these two platforms as they are the top two most widespread platforms in the US and also the top two platforms in terms of the number of ad requests sent. We next present the design of our instrumentation tools, how we selected which apps to test, and some insights from the analysis of the collected traffic data. We instrument the Roku platform by configuring a Raspberry Pi to host a wireless network. We then connect our Roku to this wireless network, and we run our software Rokustic on the Raspberry Pi. Rokustic logs the Roku's traffic by running TCP dump on the Raspberry Pi's wireless network interface, and also automates interaction with the Roku apps by sending virtual key presses to the Roku device. Since the Roku operating system does not allow apps to execute in the background, all traffic recorded during interaction with a specific app pertains to that app or the OS. With this setup, we can install and test apps in large batches, as many as 500 at a time. Our tool for instrumenting the Fire TV platform, which we call Firetastic, is a combination of existing tools. To log network traffic, we use ANMonitor, which is a VPN-based traffic interception tool from some of our past work. ANMonitor runs and logs traffic locally on the Fire TV device. ANMonitor also labels every packet with its responsible process and attempts to decrypt traffic. To automate interaction with Fire TV apps, we use a tool called DroidBot. DroidBot operates over the Android debug bridge. It maps the UI of the Fire TV app and then explores this UI in a strategic manner. Since DroidBot can communicate with multiple devices from a single laptop, we can parallelize testing of apps across multiple Fire TVs. Again, this setup enables us to install and test apps in large batches. We selected apps by crawling the respective app stores of the two platforms. For Roku, we first reverse engineered the REST API of its app store and then crawled the app store to get metadata for all available apps. We then selected the top 50 apps of each category, and this leaves us with about 1,000 apps, or approximately 12% of all available Roku apps. For Fire TV, we crawled Amazon's list of top featured apps page by page, until we reached about 1,000 apps, which is approximately 25% of all available Fire TV apps. We used Rokustic and Firetastic to test every of these top 1,000 apps of each platform for 15 minutes each. We then determined a set of unique domains across all apps of the two platforms. We find approximately 2,200 unique domains for Roku and approximately 1,700 for Fire TV. We then use our 4 block lists to label these domains as advertising and tracking services domains or not. When we only consider the ATS domains of the two platforms, we see that there is a large number of ATS domains that are unique to each of the two platforms. Even when we only consider the effective second-level domains of this set of ATS domains, we still see that there is a large fraction of domains that are unique to each platform. Again, like we saw earlier, this suggests that the ATS ecosystems of the two Smart TV platforms differ substantially. Next, we want to understand what third-party organizations dominate the ATS ecosystems of the two platforms. For this, we determined the parent organizations of the top 20 third-party ATS domains of the two platforms. We see that Alphabet, or more commonly known as Google, has a strong presence on both platforms. However, more interestingly, we see that most of the remaining organizations differ across the two platforms. This indicates that some of these companies focus on a single platform, which once again points towards substantial differences in the ATS ecosystems of the two platforms. In order to understand how the platforms differ in terms of the communication patterns of each individual app, we compared the set of domains contacted by apps that are present in both the Roku and the Fire TV datasets, which we refer to as common apps. So since app names differ slightly across the two platforms, we identified common apps by performing fuzzy matching on the app names. So for example, on the Roku side, the TechSmart app is called TechSmart.tv, but it's just called TechSmart on Fire TV. Here we show data for the top 60 common apps in terms of number of domains contacted. So blue and red indicate the number of domains that are unique to the Roku and the Fire TV versions of the app respectively, and the green indicates the number of domains accessed by both the Roku and the Fire TV version of the app. And here we notice that the common apps share very few domains, which once again suggests that there are substantial differences between the ATS ecosystems of these two smart TV platforms. We also compare the top 20 third-party ATS domains of the two platforms to those of Android, so as to better understand the similarities and differences of advertising and tracking on smart TVs versus on the mobile platform. So for Roku, we observe a very little overlap of only 2 out of the top 20 domains. Here we also note that while Android is dominated by 4 major organizations, the Roku top 20 includes a much more diverse set, including smaller organizations such as Pixelate and Teleria. For Fire TV, the story is quite different. Here we see an overlap of 9 domains, most of which pertain to Alphabet, or more commonly known as Google. So this makes sense, as Fire TV's operating system is built from Android, thus native Android ATS libraries work out of the box on Fire TV. We have now presented an overview of the ATS ecosystems of multiple smart TV platforms by analyzing data collected from smart TVs as used by real users, as well as by instrumenting 2 smart TV platforms in a testbed setting. Please see our paper for additional analysis. So we next proceed to our second research question. How effective are existing privacy-enhancing tools in preventing advertising and tracking on the smart TV platform? We address this second research question by analyzing the effectiveness of DNS-based block lists. We focus on block lists as these are universally applicable across all smart TV platforms. In particular, we evaluate Pi-hole's default set of block lists so as to emulate the experience of a typical Pi-hole user. We also evaluate Firebug to emulate an advanced Pi-hole user who applies a more comprehensive set of recommended block lists, and Firebug includes a smart TV specific sublist. Similarly, we also evaluate mother of all ad blocking to emulate an advanced Pi-hole user. So this is a huge general purpose block list. Finally, we evaluate StopAd's smart TV specific block list so as to assess the effectiveness of a block list that explicitly targets smart TVs. As a first step towards understanding the effectiveness of block lists in preventing ads and tracking on smart TVs, we first study how well each block list maps each smart TV platform's domain space. To this end, we define block rate as the percentage of domains contacted by the smart TV platform that are blocked by the block list. We observe that Firebug blocks the most domains, despite being 1/3 shorter than mother of all ad blocking. So this is interesting as it means that a longer block list is not necessarily a better block list. This is possibly due to Firebug's inclusion of a smart TV specific sublist. We are also disappointed to find that StopAd's smart TV specific list performs the worst. However, this may possibly be due to the fact that StopAd is a much shorter list than the rest of the lot. However, a high block rate could be an artifact of overblocking, meaning that the block list blocks domains that are necessary for an app to download its main content. Such overblocking may result in app breakage. As automated identification of app breakage is still an open research question, we perform additional manual experiments with 10 apps from each platform. We test 3 common apps, the top 4 free apps of each platform, and 3 randomly sampled apps. We perform 5 sets of experiments for each of these apps, 1 experiment where we don't apply any block list in order to establish a baseline, and 4 experiments where we individually apply each of the 4 block lists. While interacting with each app, we make note of ads and app breakage. In this table, we use a red cross to denote that ads were observed during interaction with the app. We also use a red cross to indicate minor breakage, which we define as minor glitches, for example to the UI, but where the app's main content remains available. We use a bolded red cross to indicate major breakage, which is when the app fails to launch completely or when the app's main content becomes unavailable. In line with our findings for block rate, we observe that Firebug performs the best in terms of blocking ads. We are again disappointed to find that StopAd's Smart TV specific block list is the distant last in terms of its ability to block ads. We also find that Pi-hole's default set of block lists seem to offer the best trade-off between blocking ads and preventing app breakage. So this is a positive finding, as the average user is likely to opt for this default choice. Moreover, this also shows that Pi-hole's community-driven effort pays off well. However, our main takeaway here is that no block list is able to prevent ads across all apps, even for this small sample set, and all block lists incur major breakage for at least one app. We next examine how well the block lists prevent tracking. We search the payload of packets in our testbed dataset for personally identifiable information, or PII for short, and then examine to what extent the block lists are capable of blocking packets containing PII. However, not all PII exposures are necessarily bad. So our view is that exposures of PII to the first party, meaning the app developer's own servers, is generally warranted, as this enables personalization of app content. On the other hand, we consider exposures to any third party as tracking related. PII exposures to the platform operator are less binary, as these could be for software maintenance purposes. However, both platform operators also engage in advertising and tracking. So in fact, Amazon runs one of the two main data brokers for targeted ads on Fire TV. Here we show a subset of the PII values that we consider and the number of apps that expose each PII value. The block rate is the percentage of domains that received the respective PII value that was blocked by the union of the four block lists. We observed that there are few exposures to the first party. The block lists seem to capture the functional nature of these exposures well, as only few domains are blocked. We find that hundreds of Roku apps send the advertising ID and the serial number to third-party servers, but the block lists do reasonably well at preventing this. A substantial number of Fire TV apps also send PII to third parties, and the block lists struggle to prevent exposures of the serial number and the device ID. We also find a very large number of Fire TV apps that send PII to the platform operator, and the block list struggle to prevent exposure of the serial number and the device ID. Now, very alarmingly, we find that almost 700 apps send all of these three PII values in a single request to what appears to be an Amazon ATS endpoint. So this effectively eliminates the user's ability to opt out of targeted advertisements by resetting their advertising ID, as this allows Amazon to relink the old and new ad IDs by joining on the static serial number. In total, we find that hundreds of apps expose PII, and the block lists do reasonably well at preventing this on Roku, but less so on Fire TV. However, the Roku numbers represent a lower bound, as we can only analyze clear text traffic on Roku. In summary, we presented an overview of the ATS ecosystems of multiple smart TV platforms by analyzing a dataset collected from smart TVs used by real users, as well as by collecting and analyzing a dataset in a testbed setting. We showed that smart TV ATS ecosystems appear to differ substantially across different smart TV platforms. We evaluated the effectiveness of DNS-based block lists and found that no list is able to block all ads while preventing app breakage. We also found that the block lists prevent some exposures of PII, but leave room for improvement. There is thus a need for additional research in improving block lists for smart TVs. Finally, thank you for listening in. Please visit our project website where you can access the dataset, and we're currently working on preparing our tools, Rokustic and Firetastic, for release.